The first subtopic is fuels and combustions. Fuels is a combustible substance containing carbon has a main constituent, which on proper burning gives large amount of heat, which can be used economical for domestic and industrial purpose. For example, charcoal, coal, kerosene, petrol, diesel, producer gas, oil, gas, and etc. The slides shown is a process of combustions, which is combined with oxygen with a liberation of heat. The reaction can be explained, which shown the formula in the slide. And there is figure showing about the process combustions. There is two types of air. Atmospheric air contain 21% oxygen by volume. Then air fuel ratio is AF, which is expressed on mass basis and defined as a ratio of the mass of air to the mass of fuel for a combustion process. The formula are shown in the slide. Then the air fuel ratio, which is represent the amount of air used per unit mass of fuel during a combustion process. The diagram are shown in the slide. The next subtopic is theoretical and actual combustion processes. There is two combustion processes. First is complete combustions, stoichiometric combustions. If all the carbon in the fuel burns to carbon dioxide, all the hydrogens burns to hydrogen chloride, and all the sulfur if any burns to sulfur. The second combustions is incomplete combustions. If the combustion products contain any unburned fuel or components such as carbon, hydrogen, carbon dioxide, or chloride, which is insufficient oxygen, mixing in the combustion chamber during the limited time that the oxygen are in contact and 3 dissociation at the high temperatures. The diagram shows the process combustions for the complete and incomplete combustions. Then the next is stoichiometric or theoretical air, the minimum amount of air needed for the complete combustions of a fuel. The stoichiometric or theoretical combustions, which is the ideal combustion process during which a fuel or a burn completely with theoretical air. And the formula are shown there. The processes combustions with no free oxygen in the products is called theoretical combustions. The next subtopic is enthalpy of formations and enthalpy of combustions. I'm going to explain what is combustions. Combustion is always enthalpic process, and this enthalpy change of combustions must always be positive. On the other hand, enthalpy change of formation can be either positive or negative, since a reaction to form 1 mole of substance can be either exothermic or endothermic. And the next is the standard enthalpy change of combustions, and the formula are shown in the slide. Then typically measured in a kilojoule mole, in which case it may further regarded as the energy released by 1 mole of the substance. The enthalpy reaction, HR, the difference between enthalpy of products at the specific state and the enthalpy of reaction at the same state for complete reaction. The next is heating value, the amount of heat released when a fuel is burned completely in a steady flow process, and the product are returned or to the state of the reactants. The heating value of a fuel is equal to absolute value of the enthalpy of combustion of the fuel. The next is higher heating value, which is HHV, when the hydrogen oxide in the products is in the liquid form. And the next is lower heating value, when the hydrogen chloride oxide in the products is the vapor form. And the formula of heating value are shown in the slide. The next subtopic is first law analysis of reacting systems for the steady flow system and the closed system. There is shown the formula for steady flow system and the closed system, and there is also about the steady flow system, which is energy input and equal to energy output. Taking heat transfer to the system and work done by the system to be positive quantities, the energy balance relation, which is shown in the slide. If the enthalpy of combustion for a particular reaction is available, that is shown in the slide. Most steady flow combustion processes do not involve any work interactions, and also combustion chamber normally involves heat output but no heat input, and the formula are shown in the slide. The next is closed systems, which is the PV terms are negligible for solids and liquids and can be replaced by the RT for the gases that behave as an ideal gas. Continue to the first law of analysis of reacting systems, which is there is example first law analysis of steady flow combustions. There are example of questions related to the first law analysis of steady flow combustions, and there is types of questions with the solutions. There is formula available, and there is the solutions. That's all. And there is another types of questions for the first law analysis of reacting systems. There is solutions available, and with the solutions and formulas. Okay, so the next subtopic is adiabatic flame temperature. Adiabatic flame temperature, which is a combustion process that takes place adiabatically with no work or changes in kinetic and potential energy, then the temperature of the products reaches the maximum. The formula are available in the slide. The adiabatic flame temperature of a fuel depends on which the first is the state of the reactant, the second is the degree of completion of the reaction, the third is the amount of air that used. The slide shown the maximum temperature encountered in a combustion chamber is lower than the theoretical adiabatic flame temperature. The process also shown there. There is example with the solutions step by step. The last subtopic is the entropy change of reacting system, which is about the entropy balance for any system, including reacting system undergoing any process, can be expressed as system input minus output. The formula is shown there. Then there is the entropy change associated with the chemical relations. The process are shown in the slide. And then there is a figure that shows at a specific temperature the absolute entropy of an ideal gas at the pressures other than the pressure equals to 1 atmosphere can be determined by the subtracting from the tabulated value at the 1 atmosphere, and that is absolute entropy values at the pressures other than the pressure equals to 1 atmosphere for any temperature. T can be obtained from the ideal gas entropy change relation written for an imaginary isothermal process between states temperature and pressure, and temperature as illustrated in the figure that's shown. And there is formula for the component of an ideal gas mixture. That's all for me. Sorry for some mistakes that I made. Thank you.